Lesson: Unsupervised learning for anomaly detection. Unsupervised learning, a branch of machine learning, plays a pivotal role in anomaly detection within cybersecurity. Unlike supervised learning, which relies on labeled datasets, unsupervised learning identifies patterns and regularities in data without pre-existing labels. This makes it particularly useful in cybersecurity, where anomalies such as cyber attacks or system breaches are rare and their signatures are not always known beforehand. Anomaly detection is crucial in cybersecurity as it aims to identify unusual patterns that do not conform to expected behavior, potentially signaling a security breach. Traditional rule-based systems often fall short due to the dynamic and evolving nature of cyber threats. Unsupervised learning algorithms, however, can dynamically adapt to new and emerging threats by learning from the data itself. This adaptability is essential in modern cybersecurity frameworks. A fundamental aspect of unsupervised learning for anomaly detection is the concept of clustering. Clustering algorithms such as k-means, hierarchical clustering, and dbScan group similar data points together based on predefined criteria. Anomalies are detected when data points significantly deviate from these clusters. For example, in network security, clustering can be employed to establish a baseline of normal network traffic. Any deviation from this baseline, such as an unusual spike in traffic from a single IP address, can be flagged as a potential anomaly. Another powerful technique within unsupervised learning is principal component analysis. PCA reduces the dimensionality of data, making it easier to visualize and analyze. By transforming the data into a new coordinate system, PCA highlights the directions where the data varies the most. Anomalies can then be detected by identifying data points that lie far from the principal components. This method is particularly effective in detecting anomalies in high-dimensional data, such as user behavior logs or system audit trails. Autoencoders, a type of neural network used in unsupervised learning, have also shown significant promise in anomaly detection. An autoencoder learns to compress data into a lower dimensional representation and then reconstruct it back to its original form. During this process, it minimizes the reconstruction error for normal data. Anomalous data, which the autoencoder has not seen during training, results in higher reconstruction errors. This difference in reconstruction errors can be used to flag anomalies. In the context of cybersecurity, one practical application of unsupervised learning for anomaly detection is in identifying insider threats. Insider threats are notoriously difficult to detect because the malicious activity often originates from authorized users. By applying clustering techniques to user activity logs, one can establish patterns of normal behavior for each user. Any deviation from these patterns, such as accessing unusual files or logging in at odd hours, can be flagged for further investigation. Another application is in the detection of zero-day attacks, which are exploits of previously unknown vulnerabilities. Traditional signature-based detection methods are ineffective against zero-day attacks as they rely on known attack signatures. Unsupervised learning approaches, however, can detect these novel attacks by identifying unusual patterns in system behavior. For instance, an unexpected spike in CPU usage or an unusual sequence of system calls can be indicative of a zero-day attack. Unsupervised learning also plays a crucial role in network intrusion detection systems. NIDE monitor network traffic for suspicious activities and potential threats. By employing clustering algorithms, NIDES can differentiate between normal and abnormal traffic patterns. For instance, an unexpected increase in traffic from a specific port or an unusual communication pattern between devices can be identified as potential intrusions. The effectiveness of unsupervised learning in anomaly detection is further substantiated by empirical evidence. A study by Chandola, Banerjee, and Kumar demonstrates that unsupervised learning algorithms can achieve high detection rates with low false positives in various domains, including network security. Additionally, a report by the Ponemon Institute highlights that organizations implementing advanced anomaly detection techniques, such as unsupervised learning, experience significantly reduced data breach costs and shorter breach life cycles. Despite its advantages, unsupervised learning for anomaly detection is not without challenges. One significant challenge is the high dimensionality and volume of data in cybersecurity. High-dimensional data can lead to the curse of dimensionality, where the distance between data points becomes less meaningful, making clustering and other techniques less effective. Dimensionality reduction techniques, such as PCA, can mitigate this issue, but may also result in the loss of important information. Another challenge is the interpretation of anomalies. Not all detected anomalies are indicative of malicious activity. Some may be benign or due to system errors. Distinguishing between true positives and false positives requires further investigation and domain expertise. Additionally, the dynamic nature of cyber threats necessitates continuous learning and adaptation of the models. This requires regular updates to the training data and retraining of the models, which can be resource-intensive. The integration of unsupervised learning with other machine learning approaches, such as semi-supervised and supervised learning, can enhance anomaly detection capabilities. For example, semi-supervised learning can leverage a small amount of labeled data to improve the accuracy of unsupervised models. Similarly, ensemble methods that combine multiple models can provide more robust and reliable anomaly detection. In conclusion, unsupervised learning offers a powerful and adaptable approach to anomaly detection in cybersecurity. By leveraging techniques such as clustering, PCA, and autoencoders, unsupervised learning can identify unusual patterns and potential threats in vast and complex datasets. While challenges remain, the integration of unsupervised learning with other machine learning approaches and continuous adaptation to evolving threats can significantly enhance cybersecurity defenses. As cyber threats continue to grow in complexity and sophistication, the role of unsupervised learning in anomaly detection will become increasingly vital in safeguarding digital assets and infrastructure.